Um, in this recording, what I'll be doing is I'll be through this playlist actually. I'll be taking you through my journey of mathematics from the very beginning for as I prepare for some of the entrance exams in India. And this would mean that we cover various topics, including things like set theory, linear algebra, uh, calculus, vector algebra, probability, trigonometry, 3D geometry, and so on and so forth. Eventually, also edging into quantitative finance, concepts related to quantitative finance like stochastic calculus and whatnot. In this video, however, I'll be focusing on set theory. Um, so let's jump right into it. So it all comes down to what are sets, right? And it's easy to kind of understand set theory as long as you get a couple of things down, right? So let's begin with knowing what is a set, right? And a set. So see what it is. Set is essentially a well-defined collection of objects, right? And what do I mean by this? It means that it can be literally any particular object that belongs to a given collection. So you need to know that when you're probably reading through a lot of material, you'll probably come across other names being used instead of objects. So objects, elements, members, they're all synonymous to each other. So so a set is a well-defined collection of objects. So what is something that I can create um, a set with? For instance, usually a set is denoted using a capital letter. So let's say we have a set A, which is defined by a collection of objects, let's say numbers, which are defined like this: 1, 3, 5, 7, right? This is a set because the objects are very clear. It has 5 objects within it, the object being a type of number that we are putting into the set. Now, this is one type of representation which we can use to represent a set. This type of representation is known as a roster form or a tabular form of a set, right? In this form, basically, when we describe a set by listing the elements and separating by the commas that we have done here within some braces, braces as in within some brackets, then that would be a set, right? So another set that I could possibly make with, say, a set B would be April, September, August. So this is a set of months, right? This is also a set because it is defining objects within that are comma separated and within braces, right? So doesn't always have to be numerical. It is just a collection of objects, and objects expands to multiple domains of what you can really define it with, right? This is one form of set that you can have. Another form that you can use to denote sets is the set builder form. And a set builder form is very easy to understand once we go through a couple of examples. In a set builder form, essentially, instead of listing all of the elements using say a comma or separation, we define them, we or describe them using describe the entire set by some special property that satisfies that is satisfied by all of the elements in the set. For instance, if I were to generalize it, if I say set C is a set of all elements X, where say P of X holds, where P stands for some property, right? So where P of X holds, right? This is a way in which you're building the set. A very good example of this is, for instance, let's say we have a set that is defined in roster form like this. Let's say A is equal to 1, 2, 3, and 4. This is the roster form of a set. The equivalent set builder form for this would be something like this, right? Let's say we define A to be such that its elements are such that it belongs to the set of natural numbers and all elements are less than the number 5. And this satisfies the properties that all of the elements of set A holds. So this is the set builder form of the first set. So when you define it by a formula or a property, that all of the elements holds, then it is a set. So how do we read this exactly? Let me clarify that. So the way we read this is that we say that A is the set of all elements X such that is either denoted by the colon or a dash line, a line like this, a vertical line like this. So it reads as such that has the property X belongs to the set of natural numbers and X is less than 5, right? So I hope this is clear. Now, from within this, you would have realized that there is a standardization I can come up with, right? Sets are usually defined by capital letters. Okay, so let me write that down. Sets are usually defined by capital letters. Let's say, for instance, A, B, and C, etc. Right? And their elements are usually indicated, and their elements are represented by small letters. And I will use something like, say, A, B, and C respectively, right? If A is a member, if let's say if there's an element A that is a member of a set, we denote it as like this: A belongs to A. This stands for, if you probably got it from the earlier monologue, this just simply means to belongs to. So A belongs to A, capital A, or A is an element of A, or A is a member of A. Right? If A is not an object, or if no A is not an element or a member of A, then we would write it like this: A does not belong to A, right? Or it also stands for A does not belong to A is not an element of A, or A is not a member of A. Those are three ways in which I can write it, right? Now, one of the next important thing that you would probably need to know are the types of sets that exists. There's quite a few. The first one is an empty set. And like you would probably infer, an empty set is a set that has nothing in it, right? So a set which does not contain any element is called an empty set, right? It's also called a null set or a void set. And we usually denote this. This is denoted by a phi symbol like this, denoted by phi, or like as before, like a curly braces, but with nothing in it, right? So, for instance, I could define an and a null set in the following way. Consider this. Let's say A is equal to the set of all elements X, such that X belongs to the set of natural numbers and X is between 3 and 4. This is essentially a null set or a void set, because the set of natural numbers is strictly numbers like 1, 2, 3, 4, 5, and so on and so forth. And so um, there isn't any natural number that exists between 3 and 4, right? And that is why this set would be an empty set or a null set or a void set. Another example I could probably come up with for a null set could be something like, let's say if we have a set B, which is defined by the set of all elements of X, no, set of all elements of X such that X has the property that the 1 plus X squared is equal to 0 and X belongs to the set of real numbers, right? This is a null set. Why? because you can't possibly have a positive number that exactly cancels out or that satisfies this property, right? Exactly cancels out one in a way that gives you zero. The only way one can be canceled out to give you zero is if you have a minus one added to it. But there's no way a square of a number, which is always positive, will give a number that adds to zero, right? And that is why this is also a null set or a void set or an empty set. Then you have what is known as the singleton set. A singleton set is, oh, before I cover the singleton set again, one common mistake made by most people when they try to conceptualize this is, for instance, if you have a set that is defined like this with zero in it, this is not an empty set because it contains an object and the object is zero, right? Zero is also an object, and often poorly people think that zero has no value and therefore it's not an object. That's not the case. It is an object which may or may not necessarily hold any value, right? So an empty set, um, a zero set is not exactly a null set, right? It is a set that exists. A singleton set. I'm sorry, I think my iPad is glitching. Okay. A singleton set. A set which has only one element is called a singleton set. An example of this would be, again, I could probably extend something from our earlier case. For instance, let's consider a set of all elements of X such that X belongs to the set of natural numbers and X is between and 4. So the only element that exists in this way that satisfies both properties is 3, right? And so there's only one object that this set has, right? So I can write it also equivalently like this, equally like this, right? So this is a singleton set. The next is there are then finite sets. A finite set is a set which has a set which is like has a definite number of elements, or if it's empty, right? Then both are finite sets. So in that regard, an empty set is also a finite set, right? So a set with finite elements, a definite number of elements is a finite set, right? So, and to always like to know whether it's an empty, subcategorize whether it's a finite set which is not empty, you would also need to know something known as the cardinality of a set. The cardinality of a set represents the number of elements which is there inside the set, right? So cardinality refers to the number of distinct elements of the finite set. So for instance, if you have a set defined like this, set of A, which is 1, 2, 3, 4, 5, so on and so forth, the cardinality of this set, often denoted like this, n of A, is essentially 5, because there's only 5 objects within this, right? Another example I could have of this is, say, let's say we have a set D, which is defined by 4, 3, 1, right? The cardinality of this set is 3, because there are only 3 elements within the set, right? The next type of set that we are interested in is something known as the infinite set. And like the name already suggests, given our discussion so far, you can just say a set which is not a finite set is essentially an infinite set, right? So it's a set basically where the counting of elements does not really come to an end, right? So you can't really count. So you can't actually find the cardinality of the set. right? A very good example of such a set are the points on the plane, because you can't really count the number of points in a plane. It's like there's like an infinite number of points that you can have. So the points on a plane cannot be counted. And so will become a finite set, infinite set, sorry. Then there are what are known as equal sets and equivalent sets. Um, let's just cover that. Right? So an equal set is one in which if you have two elements, or if you have a number of sets, say, let's say we have set A and set B, and they're defined by a set of elements as it would be defined in the case that it is, right? The two sets are said to be equal to each other only if the elements that are there in A are also the elements in B, and every element in B is also an element of A, right? In that case, when you say if x, if an x belongs to A, then x would also belong to B. And let's say if there exists some element z that belongs to B, then it would also mean that z belongs to A, right? Then A and B are considered to be equal sets, right? So we can then say that A is equal to, right? An equivalent set, however, is one in which the number of elements in two sets are equal to each other. They may not have the same element, but if the number of elements are the same, then they are said to be equivalent sets. Right? I hope that makes sense. I'm not going to write it down. It's very straightforward, right? And then we have the seventh definition, which is important, which is seventh definition. It is important, which is subsets and supersets. Let's say we have a set defined as A is equal to 1, 2, 3, 4, and 5. And we have another set B, which is equal to 1, 2, and 3. Right? Since all the elements of B are within the set of A, and which is a part of A, we would say B is a subset of A, right? Or equivalently, if I define it like this, like if I say A, this also holds true because B is a subset of A. That means A is the superset of A. This roughly can be interpreted as B is a subset of A. And here, this is where A is a superset of B, right? Okay. The next thing, a concept that is often tried inextricably to the set theory is of intervals as subsets of A, right? Which we will cover in the next subsection.